Before we get to the Taylor series, I want to talk about some other famous series in mathematics. Let's start with the P series. So the P series is the sum from n equals 1 to infinity of 1 over n to the p. So we see here that n is a natural number. P, the exponent, can be any real number. If we plug in n equals 1, we get 1 over 1 to the p, which is 1. And then n equals 2 would be 1 over 2 to the p. N equals 3 would be 1 over 3 to the p, etc. So this infinite sum is called the P series. And it depends on what the value of p is. So the first thing we can see is that if p is a negative real number, then the terms in this series are growing, and it must diverge, because we need if for an infinite series, we need the terms to go to 0 for it to converge. So p has to be positive, and the larger the value of p, then the faster this series will converge. So here I want to determine at what is the dividing line for p. So for p larger than some number, it converges, and for p smaller than some number, it diverges. To do that, we're going to make a comparison of this series with an integral. Let me show you the graphs. So if we plot the function y equals 1 over x to the p, now replacing the natural numbers by the real numbers, we get a graph. If p is positive, then it's a decaying function in x. And in this first plot here, I draw rectangles where the upper right corner of the rectangle touches the graph. And in the lower plot, I draw rectangles where the upper left corner of the rectangle touches the graph. So here we look at the area of the rectangle. So the width of the rectangles are all 1. So the area is just given by the height. Here the height is 1. Here the height is 1 over 2 to the p. Here the height is 1 over 3 to the p, etc. So the area of these rectangles is just the P series. Again, if we look at the bottom graph, the height of the first rectangle is 1. The height of the second rectangle is 1 over 2 to the p. So again, the area of the rectangles is just the P series. Okay. We want to compare the P series then to the area under the curve of this function. So if we look at this function from 1 to out to infinity, the area under the curve then will be larger than the area of these rectangles, but the area of the rectangles starting at a height of 1 over 2 to the p. So that lets us write an inequality here that the sum from n equals 1 to infinity of 1 over n to the p, our P series, the sum of all these rectangles is less than, if we exclude the first rectangle, so it's less than 1, which is the first rectangle, plus the area under the curve from 1 to infinity. So plus this integral from 1 to infinity of 1 over x to the p dx. Okay, so that gives us our first inequality. However, if we look at the second one, the integral here from 1 to infinity is smaller than the P series. So we get the integral from 1 to infinity of 1 over x to the p dx is less than the P series. N equals 1 to infinity of 1 over n to the p. Okay, we can combine these two inequalities. If we start with the bottom one, we get the integral from 1 to infinity of 1 over x to the p is less than the p series, n equals 1 to infinity of 1 over n to the p. And then the sum from 1 to infinity of 1 over n to the p then is less than, from the top inequality, 1 plus the integral from 1 to infinity of 1 over x to the p dx. You should never forget your dx in your integral. So I'll put it there. Okay, we have dx here. Okay, so we have our bound then for our p series. So the key here is, how does that integral behave? Let's consider the case where the integral diverges. If the integral diverges, then we have the p series is larger than infinity, so then the p series has to diverge. Now let's consider the case where the integral converges. If the integral converges, then 1 plus the integral also converges. So then the p series is less than a finite number. But the p series is a strictly increasing, the series itself is increasing as the limit goes to infinity, because every term is positive. So as we sum, this is increasing, but it's less than a finite number. So then that the p series then must converge to a value. Okay. So the key here then is to determine whether this integral converges or diverges. If p equals 1, it's a special case. It's the integral of 1 over x dx. That's a logarithm. So let's consider first p not equal to 1. So p not equal to 1. Then we're looking at the integral from 1 to infinity. I can bring up the x, so x to the minus p dx. We can use the power rule here, so we know how to integrate that. That's x to the minus p plus 1 divided by minus p plus 1, and that's evaluated between 1 and infinity. The lower limit is clear. That's just a finite number. So the problem here is in the upper limit. So let's rewrite that. So we can factor out the denominator. So 1 over, let me write that as 1 minus p. And then the lower limit here will be minus 1 to the minus p plus 1, but minus 1 to some power is just negative 1. So the lower limit there is just negative 1. And then the upper limit will be the limit as x here goes to infinity of x to the minus p plus 1, or 1 minus p. Okay. So the question is then, when does this limit here diverge, and when does it converge? So we can look at that. So if p is larger than 1, then the exponent is negative. So then as x goes to infinity, it goes to 0, so that the integral converges. So there's two cases. So if p is larger than 1, so p is greater than 1, then we will get converge. So the opposite case, where p is smaller than 1, so p is less than 1, then 1 minus something less than 1 is positive. So if p is less than 1, the exponent is positive. So then as x goes to infinity, it goes to infinity, so this diverges. Okay? So p equals 1 is the dividing point here. Larger value than 1, the p series converges. A smaller value than 1, the p series diverges. We know that the p series diverges when p is negative. So the remaining case is the borderline case. So p is equal to 1. Then this integral is x to the minus 1, so it's 1 over x dx. X is positive, so that's just the logarithm of x, right? And the limit is 1 between 1 and infinity. We know that the logarithm of 1 is 0, but the logarithm diverges at infinity, so this 1 diverges, so this goes to infinity. So we can conclude then that the borderline case diverges. So it converges if p is larger than 1, and it diverges if p is less than or equal to 1. So let me summarize. We tried to figure out the value of p for which the p-series converges. Okay? To do that, we can compare the p-series to an integral, bound the p-series by an integral. So if the integral diverges, then the p-series is larger than that integral, so must also diverge. On the other hand, if the integral converges, then the p-series is less than that finite number and must also converge. So the p-series then converges if p is larger than 1, and it diverges if p is less than or equal to 1. A little bit complicated. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.